I have started this lecture on Friday during the tutorial time, but I have not finished it. And since this section is very important, as you need these points for midterm and final exams, I just want to go through them, just making sure that I have explained the concepts so you can understand them and you can solve problems based on these particular equations. So the topic that we have started looking at on Friday was the Joule-Thomson effect, or simply the process of what's called as throttling. The Joule-Thomson effect tells a story about a particular fluid undergoing some changes. So it tells us whether or not a fluid cools during expansion at constant enthalpy. And it's very important that you understand that the process is a constant enthalpy process. Here I am showing you something that we have discussed in class. You have a fluid at T1 and P1 passing through a restriction valve, and it exits as T2 and P2 as shown here. And since the energy balance that we have done clearly demonstrated that the process is taking place at constant enthalpy, what we are going to do is start from the dH expression here, and that's what we are after. And because enthalpy is constant, dH is going to be 0 because the derivative of a constant is 0. And so we'll set this side of this equation 0, and then we rearrange the rest of the equation so that we'll end up having this expression here. So this expression, which is given a special symbol, which is mu jt, J stands for Joule and T stands for Thomson, so it's mu jt, is defined as the partial derivative of temperature with respect to pressure at constant enthalpy. And if you rearrange the above equation, you basically get this expression over here. And so this is actually the expression that will tell us whether a fluid will cool or not when it's undergoing this expansion process. So now it's important to actually get an insight by writing this equation a little bit differently. Here we have mu jt, which is over here. It's defined as, and this symbol is just defined as the partial of T with respect to pressure at constant enthalpy. And if you actually convert this derivatives notation into a finite difference notation, you get delta T over delta P at constant H. And then if you go back into the process and look at it, it just means that T2, which is, remember, T2 is the outlet temperature, minus T1 over P2, which is the outlet pressure over here, minus P1, which is the inlet pressure. Now, that is evaluated at constant enthalpy. And so the question that we are going to ask ourselves is this quantity a positive quantity or a negative quantity? If you look at the denominator here in this expression, P2 minus P1 is always going to be negative. The reason is that flow is possible when you have a pressure drop, and then therefore you have now P2 minus P1 to be 0. The fluid is expanding, and when the fluid expands, of course, the pressure drops, and so P2 is always less than P1, and that's how flow is possible. And so the difference between P2 and P1 is always negative. The top one, T2 minus T1, it could be positive, it could be negative. If T2 over here, if T2 here is greater than T1, then what will happen is that T2 minus T1 becomes a positive quantity, and then mu jt over here will be positive because you have a positive quantity over here. I'm sorry, mu jt will be negative because you have a positive quantity up in here and a negative quantity down there. However, if T2 is less than T1, so which means if the exit temperature is smaller than the inlet temperature, obviously the fluid must have lost energy somewhere in the process, and in that case this difference will be negative. So you have a negative on the top and a negative at the bottom, and mu jt then becomes positive. So what it tells you is that mu jt, which is the Joule-Thomson coefficient, is positive when you have cooling, and it is negative when you actually have heating. So that's a concept in here. So you have to understand that pressure is always negative down here, and then the temperature difference is really what determines whether you are going to have cooling or heating. Now, if you look at this process, you may be asking, how do we then determine experimentally? And I know that this course doesn't have an experiment, but it's just, go through the process, how one could generate the appropriate temperature and pressure so that the fluid could be heating or cooling depending on the situation. So what we have in here is we have an inlet T1, P1, and an exit P2, T2. So experimentally, the way these data are generated is that you have this point down here, and that is your inlet condition. And that is given by P1, and the corresponding temperature, if you draw a horizontal line, it will be somewhere there. So you have this point is going to be T1, P1, and that is the inlet condition. And then you expand it through the restriction valve, and when you expand it, you will measure temperature and pressure. So obviously pressure is going to drop, and so it's going to come down this way, because remember the exit pressure is lower than the inlet pressure. And so we know that P1 is going to be smaller than, P2 is going to be smaller than P1, and so what we'll have is a point somewhere in here. And obviously temperature, it may have gone down or it may have increased. In this particular case, you can see that the temperature also increased, and so that is experiment number 1. In the second experiment, what you'll do is you will keep the inlet condition, and again, so your inlet is fixed, it's P1, T1, then you change the exit condition here. So the exit condition here is obviously different from down here, and the question is, how do we actually bring this exit state to the value that we see over here? Well, you can do that. What you can do is, this is your porous plug, so you can just simply change the porosity of this plug, so you actually are affecting the outlet temperature and pressure. Or if this is a valve, by just simply changing how much you can open the valve, then you are changing the exit properties of the fluid, which is P2 and T2. So you can just play with this porous plug by just changing the porosity, or if you have a restriction valve, you can just simply open the valve 1/4 or 1/2 or 3/4 and so forth, and then you can see that P2 and T2 are going to be different. But remember that the inlet state is exactly the same, P1, T1, which is shown down here. So you have now the second experimental point. And so in the third one, what you do is you go, and again your inlet condition is the same, but then you change the exit condition by changing this porosity or by opening and closing this valve to a certain point. And so if you can just go through this experiment, then what you'll generate is a curve like this. So you're measuring T2 and P2 at the exit states by changing either the porosity of the plug or the degree to which you are turning the valve. And so along this line, then the enthalpy is constant. So the H constant line here shows you that along this path, the enthalpy is constant. So this is just for one inlet condition. Now what happens if you change the inlet condition? So I'm going to show you in the second slide, figure in here. So this is the the line that we actually discussed now. But then if you change the inlet condition here, it will be a different P1 T1 compared to the previous one. And then we can just go through that experiment by changing again the porous plug or the restriction valve. And again, we will generate another one. Then we go and we change the inlet condition into a third one. And again, it will be P1, T1, but you know, it's a different value compared to these two other lines. And then once we have the, you know, that fix that value, then we just simply change the exit state by opening and closing the valve, or by changing the porosity of the plug, and so we can go along these lines over here. And so you can actually generate these different lines, and what you do is you connect the data points and you smooth it out, so you can see this smoothed out curve or curves. And so one important thing about these curves is that the slope actually changes. So you can see that in certain region of the slope, sorry, in certain regions of this plot, the slope is positive. So you can see that this is actually a positive slope. And then it passes through a flat region, which is a zero slope. And then it goes downhill where the slope is now negative. And the same thing can be said about this line. You can see that the slope is positive in this area, and then the slope becomes zero here, and then it becomes negative as you go into this region, and so on and so forth. So what you do is you draw an artificial line around the zero slope data point. So this is the slope for this line where it's zero. If we had another line, it would be somewhere here. If we had another line, it would be somewhere here. For this particular one, it's here. And then you draw this line. And so what the dotted curve in here, what it shows you is actually, it shows you the region where mu jt is positive and the region where mu jt is negative. In the previous slide, I already explained it to you that for cooling, mu jt must be a positive quantity. And then therefore, when mu jt is positive, then we have T2 is going to be less than T1. When mu jt is less than 0, which means mu jt is now negative, and you can see that the slope is negative, it means that T2 is actually greater than T1. In that case, we actually have that fluid heated up during the expansion process. And so this is the manner in which the experiments are designed, and the experiments are tabulated, and this types of curves are generated. Another way to look at it is for mu jt greater than 0, we have a situation where obviously the fluid is cooling, and cooling is possible when the net attractive forces dominate in the fluid at that condition. When mu jt is less than 0, then the net repulsive forces dominate the fluid, and then therefore the fluid will actually heat up when it exits the porous plug or when it passes through the restriction valve. However, there will be a situation where mu jt is 0, and these are the points shown in here. Okay, so here you have a slope of 0, here you have a slope of 0, here you have a slope of 0. And so at these points, mu jt is 0. When mu jt is 0, what it means is either we are at the Boyle's temperature, if the fluid is described by the Veyral equation of state. We know that at the Boyle's temperature, the second Veyral coefficient is 0, and then therefore the equation becomes an ideal gas equation. And the second case is where we have the ideal gas situation here. But generally, these points over here are actually called the inversion line. These points pass through the inversion line, where to the left of this inversion line, the fluid is obviously cooling, but to the right of the inversion line, the fluid is obviously heating. So this explains that a particular fluid may actually heat up if you pass it through such processes. And I know that in the first thermodynamics course with Dr. Rohani, you guys have worked a number of problems on the refrigeration cycle, but understand that any refrigerant could actually heat when it comes out of the expansion valve unless it's properly designed. And in fact, that is the case for these systems. In the next lecture, I will be adding some additional notes on the speed of sound, but this should be enough for now.